Okay, so now we'll start our second set of lightning talks. I'll also keep it short and enforce 10 minutes for the presenter. I'll give you guys a 3-minute warning as well. So, but I'll ask you guys to introduce yourself and make the presentation. And the slides are in a single deck, so just move on. Thank you. And we'll do the questions afterwards.
Good afternoon. It's my pleasure to present our work here. I'm Wei Xiong, come from National University of Defense Technology in China. And our team is supported by the High Technical Research and Development Plan in China. What I presented here is parallel geospatial raster data I/O modular we called HiGeo in the high performance geographical information system. And this is the outline. First, I give the motivation of our work, and then is our developing road. Some implementation details I will shown later. At last is our future work. As we know, the hardware becomes more and more faster, and the computation model become more and more efficient. So the spatial data I/O is increasingly becoming the bottleneck when we are in the data-intensive applications, when we do some spatial analysis, visualization, and data management, and some spatial information service. A traditional data I/O method are facing these two challenges. The first problem is the accuracy. GDAL is a widely used data model to process the raster data I/O. But when we use the GDAL in the parallel environment, if we partition the data in a raw-wise, the output is correct. But when we using the column-wise or block-wise data participation, we can see this is the incorrect output. There is some hole, there is no data in this area because when parallel processes is access data, it is some conflicts. And the second problem is efficiency. We can see the lower graph. The left part is the user view. This is the parallel processes, and P0 is read and write the block 1, 2, and 5, 6, and process P1 read and write the block 3, 4, and 7, 8. But in the actual file view, the block is organized sequence in the disk. So when the process P0 write and read the block 1, 2, and then the process P1 read and write the block 3 and 4. This produced a much small and now continuous I/O requests to the disk. So it's reduced results the poor I/O performance. And this is the developing road of our team. First, we developed the initial version of HiGeo based on the GDAL. In this version, we read the data parallelly and write the data serially. So it is not a true parallel version. So we developed the HPGFS version. This is provide a parallel file system, just like the PNetCDF or HDF5. But in this file system, more applications we found in practice, more applications is using GeoTIFF file formats. So we tend to go back to the HiGeo, and based on the tau DM to implemented a parallel version of HiGeo. But in this version, the HiGeo can only support the TIFF format and a simple data type. Then we go back again to the HPGFS, and we implemented a GDI drive for HPGFS. So we can use HPGFS to transform from any formats that the GDI supported. And now we developed the HiGeo version 0.3. Why there is so many versions of HiGeo? Now I explain the reason. In the first plan, we implemented the HiGeo, and the algorithm in our team. There is 11 university and institute is responsible to implement the geographical precision and analysis algorithms. So these algorithms use the HiGeo to read TIFF data and write TIFF data. And our visualization engine, which is implemented based on the MapNIC, can render the result data directly. But this HiGeo version is not parallel. So we implemented the HPGFS version. In this use mode, user must, the algorithm must process the data format is HPGFS. So various geospatial raster data format must be transformed to the HPGFS format. And if we want to render the result, we must transform the HPGFS to any format that MapNIC can read this. So although the performance of I/O is efficient, but the transform cost is expensive. Which is better? We can see the comparison between the HiGeo, previous version HiGeo and HPGFS. HiGeo can compatible with our visualization engine, but it is supported simple data format and data type. And if using the HiGeo, where the algorithm must be rewrite. Whereas the HPGFS is have the same interface as the GDAL, and the algorithm doesn't need to rewrite. So the shortcoming of the HPGFS is the transform cost. In our teams, in our project, there is another solution I can show like this. There is 4 processes, and the data is partitioned as 4 blocks. Before the process writes the block to the disk, we can exchange between the different processes, such as, for example, in the process P0 and for process P1, we exchange the blue and the red part. It represents different rows of the block. So we exchange the blocks between the processes and then write the block to the disk is continuously. But the communication cost is increased. So the ideal use mode of HiGeo is like this. We use GDAR to read the geospatial raster data. So we can read any formats of the geospatial raster data. And we write the data as the TIFF format and using the file view, which is the MPI-IO, which is integrated into the MPI-IO. And the visualization engine can render the result directly. This is the data structure of the HiGeo. It is very simple because we are just responsible for the data I/O. So we just need to get the metadata, set the metadata, and write data, parallel read and read data. In this use mode, we can see different processes exchange metadata only and write and compute and read the data separately. So what is the file view? File view is integrated in the MPI-IO. It is efficient parallel I/O mode. This is the example of a file view. We can see in different MPI version, the file view set is may be different. This file view we are implemented in the Open API. Oh, yes. And the left part is the performance comparison of file view and with not file view and GDAR two-phase methods. The future work is that the data I/O is become more high volume, high concurrency, and high extensibility. So the next we want to supporting more data format, testing more data format, and we want to support the parallel vector data I/O. We want to use the distributed and big memory. That's all. Thank you.
Next, Junjun. Thank you.
Oh.
Thank you, CyberGIS, for giving me this opportunity to present my paper. The topic was, it's a big topic right now, but it's only exploratory work at the moment. I hope I can bring some ideas to this talk. So my presentation will be outline. This is the outline of my presentation. First, I'm introducing some background information and the motivation of this work, and then the methods and the workflow, and then present some preliminary results, and then later is the future work. So the topic starts with a very simple idea, very, very simple. It's about the natural city. So we all know cities. Cities are human settlements. It's where people do all kinds of activities. It's in human activities. So the definition of natural city is kind of different from the official definition of, that's in terms of the shape of the city boundaries. So when you talk about Illinois and Los Angeles, you're referring to some certain shape. But natural city means it's actually the human active space where humans doing their activities, all kinds of stuff. And it can be dynamic, it can be evolving from time to time. People migrate from this place to the other place, so their settlements changed. So they form another shape of city. And that kind of city we were referring to natural city. And why natural city should be considered? Because when people do the analysis of census data-related research, like sometimes people has to interpret the census data, which is aggregated on some level into different, more detailed area. People using decimetric mapping, this kind of methods to do the tricks. But since natural city is already the active space of such, so we don't need to, it's a natural, like we can directly use the concept of natural city. And you can do the neighborhood delineation, community delineation, like livelihood. It's a social online community detection kind of software, website. You can check out. And the dynamic nature allows the researchers to study the change of city over different time period. So the motivation is there's a large body of studies already going on into this topic about the natural city. People using the network, the road networks, so people see where the roads connect most. There's supposed to be a human settlements, in a way, in an analogy. And some people using the social media, like a livelihood project. And we come from the aspect of nightlight image, satellite images. So the availability of the global scale nighttime light image covers from 1992 to 2013. It's a long 21 years time span, and it provides a global coverage. And previous research, well, why we're doing this such in the CyberGIS domains, because right now, because the limitation of computing, the computing limitations, the current study only can go as far as the country level. There's too many polygons to process, too many images to merge, to extract. And previous, my use of the country level using ArcGIS and Oracle Spatial kept me all night long, like I can't sleep. So now I come to the CyberGIS platform. Yeah, maybe it's a good idea to explore the high performance platform to do because of the high performance and the scalability to dealing with those big satellite images. And right now I'm talking about the light image, like I downloaded from the NOAA, NOAA.gov. So this is an image of year 2012, nightlight time image of the whole world. So where those light pixels are referring to the people are living, and we can extract the natural cities, the shapes from those pixels. And we are looking from the fractal dimension right now, because it's an exploratory work. We are looking at the fractal dimensions. So fractals, like basically the idea is very simple again, because the scaling of probability in the world, in every phenomena in the world, is there are more small things than large things. There are more poor people than rich people. So we're looking at the heavy-tailed distribution of those the objects, the cities of the globe, and it was like similar approach. It was inspired from Michael Betty's the theory of city size. You see there the straight line illustrates the power law distribution of the size the population and the accessibility. So when you, it's basically the power law. I'm not going into detail about the power law, but basically it's because the scaling probably richer, smaller, bigger. The distribution is very heavy-tailed. So, and for this approach, we were using very simple, again, very simple approach using the box counting. So basically, we choose a common bounding box for those 21 years, the cities as a common bounding box, right? Then we slice them into different grids. And the factor we choose is 2 right now. It's 2 square, 4, 8, etc. And using because we're using the CyberGIS platform, we choose the Spatial Hadoop to do the experiments. So the workflow will be: we take the light image, we import into the HD into the Hadoop format, and we determine the common box, and we use the latest year as the reference layer, so you use that one as a mapper, and then on the reduced side we will do the overlapping to detect those small cells that intersected with the reference layer. Then we export and then do the power exploration. In this case, we're using a case study of China. So the red one is Beijing. So you see on the right side, the official definition of Beijing is in green in that area, but the satellite image only shows this, the gray areas in different years. So that's the difference. And then we do the fishnet cutting. That's 128 scale, and then we intersect the points to count how many pixels are there in this year. And this is preliminary result, like showing fishnet of Shanghai city. So this year, 1992, 2009, this 10 years range to see the difference. So in 2010, you see a very straight line. It seems the development of the city. It seems the development of the city is really getting diverse. Like bigger city the bigger size getting even bigger, smaller size maybe disappears in this. And this is the same. This is another one for Beijing. Okay. For the discussion, we will also consider some social media data for validation of the social activities, because right now we only rely on the pixels of the light image, maybe not accurate enough to do the extraction of the cities. And we need to incorporate some other ways like the road junction. The last one, I just want to show on the left side is the road conjunctions. So all the road in China, the conjuncted, and the density map of the conjunction looks very like the nighttime image, but somehow we can overlap in them and can get rid of some places to get more accurate natural cities. That's what we're going to explore in the next stage. Thank you. Before let me go, I want to thank the foundation agency, National Foundation Agency, and that's our CG lab. And thank you.
David.
So this is going to be slightly different. This is a design talk at a CyberGIS conference, the other way around. I'm David Tulloch. I'm from the Department of Landscape Architecture at Rutgers University, the State University of New Jersey. This is one of the landmarks in that state. This is the Pulaski Skyway. When it was built in 1932, the Pulaski Skyway was at least written up as the most expensive bridge ever built. 3.5 miles long, soaring through the air. It was grand. It received engineering awards. It was stunning. People just drove it to drive it. It crossed 2 different rivers. You'll notice another bridge way off in the distance. It accomplished so much and was actually seen as an economic miracle, cutting the drive from Newark to the Holland Tunnel in half, saving money and gas at a time when that really mattered. It was a bridge that was perfect for its context. Infrastructure that served a really special purpose in a context where it worked. But the New York Times recently wrote about it, saying its entrance ramps and lane widths dangerously outdated, its roadbed and concrete railings crumbling so badly that the state has installed netting to catch the falling debris. It doesn't fit the context anymore. Right now, the bridge is almost completely closed for a few years of a complete overhaul. So that hopefully it will fit that context. We need infrastructure for geodesign that fits our context. And I want to talk about that. Mike mentioned a few sort of heroes of geodesign days past. I want to mention a couple others. Phil Lewis at the University of Wisconsin in 1964, not using GIS at all, had his students taking symbols that he and they created to represent different landscape values. These students went out into the landscape of Wisconsin, created a statewide map, lots of beautiful cutaways and close-ups. They mapped out all over the state where these values were. In an idea that really is very parallel to what we still think of today. They were collecting data, creating maps that would shape design, but of course, on paper or Mylar. And usually just yesterday I got a note that a student at the University of Wisconsin-Stevens Point named Dan McFarland has put it on ArcGIS.com so we can all go back to that 1964 map and really enjoy the complexity of what those students were doing. Another one of my geodesign heroes from Wisconsin watched what Phil was doing, and 4 years later in 1968 taught what, as far as I can tell, was the first undergraduate studio in landscape architecture to use GIS. 1968, the students in Ben Neiman's class developed a database, again, designed to guide design and policy decisions about that landscape. So it's with that kind of thinking about geodesign things, it's not new, but it's really changed. And it's changed in a way that we need a different kind of infrastructure to support it, because as each of these projects move forward, another project that the Wisconsin folks did, this is the eastern part of the state, was used to guide a power line routing network, really. As they did this, it would then get locked away when they were done, right? You take the tape off the machine and set it aside. It wasn't done in the kind of context we have today, where data moves and we share, where they got lots of data from other people. The students created all the data in the system, then they saved it, and saved it in a closet. By 1980, the vision for landscape architecture that Landscape Architecture magazine showed us was grand and beautiful. Every landscape architect would have the ability to use GIS, Raster in this case, GIS at the desktop. This was a really visible image that hung around for a few years. But again, without a real infrastructure to support it, landscape architects did not embrace this. So geodesign has moved ahead a little. I'll show you a couple studio examples very briefly with lightning speed. But we're now thinking about it in ways that raise ideas like computer-mediated design, and doing that with least cost path analysis. But usually when I give a group of landscape architects the reins of GIS, they do something like this. This was a 21-foot by 7-foot poster display that my students made of their inventory of the landscape, and then later complemented with another 21 feet of analysis that they tacked on for the Stony Brook Millstone watershed. Lots of information, and they can make it look great, but it's when they start to really interact in ways that shape the design that are fun. So this was quite a few years ago now, right before Google Earth came out. Our students began working with 3D routing of trails at Bear Mountain State Park, in fact, the trail, Appalachian Trail. And they began to try to let the computer tell them where it could go. Well, they knew not to trust it, but they did it. And then would do fly-throughs and lots of fun. And so coming back to that, much more recently, I've worked with a student named Jeremy Fisher, where we've been exploring the idea of least cost path analysis, which has been used for a while for trail routing, to guide the creation of alternatives. And we can, the phrase the GeoPlanner guys used yesterday was we can pull different levers to get different results. And Jeremy started really trying to see what we could do with this. And we ended up coming with with just 2 levers at different levels, 49 different results that took him a long time to generate. And this is where I come back to, boy, CyberGIS, how great would it be to generate 1,000 of these playing with lots of levers. And in a meaningful way, we're still going to go out and look at and test it and play with it. But the other thing that strikes me about geodesign right now is so many familiar GIS experiences are new to a whole new group of people. I look back at this wonderful old paper by Will Craig. If you don't know it, I encourage you to look it up. It's free online at the ERISA Journal. Why we couldn't get the data we wanted. I feel like we could give it out at the Geodesign Summit next year, and a lot of people would be still stunned. They come here, and I couldn't believe my county wouldn't share the parcel data that they already had made. Yeah, I know, we've been talking about this for a long time. Other familiar experiences are suddenly realizing that we have to really think about workflow again. And one that I really want to mention for a second is the social equation, which is thinking about how people fit into how we think about GIS. John Mayo, the IT genius who ran the Bell Labs, had this model that said a good innovation has to get through both the technology gate. It has to work, right? You have to somehow get the data into the system. Everything has to work. Can't blue screen. And then a social gate, which is people have to actually be able to use it and want it and desire it. There's 2 rivers you have to cross. Okay? This bridge has to get us across both. Okay? Now, this bridge that I'm showing you right now is out of context, right? I've changed the background a little. And I feel like sometimes, some of what I hear about CyberGIS, for geodesign at least, still feel like it doesn't fit the context. What could we do to make that work? What can we do in particular, I would say, by the way, to avoid those concerns and to keep other designers from even learning the lessons that we also painfully learned in the past? It's the things we've heard today. This is, by the way, I'm not being repetitive. It's concurrent validity, that I'm saying the same things that Jack and Mike have said about this, models and collaboration. So I broke it down into the categories of, it is about tools still, but tools with immediate response. It's not just that designers are impatient. They have an idea. They're trying to think about shaping, and interrupting that changes the creative process. We have, again, we've seen the opportunity to integrate models, and we've talked about the collaborative opportunities and dashboards that we saw yesterday. But also, this idea of beginning to allow the computer-mediated solution to emerge through what we in design call parametric design. We're actually setting some parameters and letting it happen and changing it and changing it and changing it. It was a really hot trend in architecture a while ago, and landscape architecture missed it because we didn't have CyberGIS to help with the computations. One of the things is guidance. Like I said, I think the geodesign is getting enough steam now that designers are at least lessening the degree to which they say, we need it this way, we need it to work exactly like this, and looking for guidance. What can be done to help us? What could we do differently to fit into this, but also feeding them case studies on how this works. Maybe CyberGIS workshops for landscape architects and geodesigners. And data. And really when I talk to landscape architects and why they don't do this, it's because they think the data's not good enough. They want live data. Crowdsourced data would blow them away. For different kinds of data, we've invested so much in the wrong data for them in this country. That's beginning to change. And what we really want as designers is a bridge that works in context, right? That connects the geodesign process to the amazing information that's out there. It's got to get across 2 rivers, not the Hackensack and the Passaic, but the technology gate and the social gate. It's got to be something that designers can make sense out of, but it's also got to last. Hopefully it won't be like this where we just have to shut it down at some point in the future for 2 years. It can hold up, and it has to be resilient because designers are like hurricanes. They're tough on everything. So having said that, this morning, I think Mike said, I think I was right, the GIS is about what is, and geodesign is about what could be. Well, CyberGIS, to me, seems to be about how we could get there. Thank you.
Good afternoon, everyone. I'm Pengxiang. I come from Wang University, and now I'm a visiting scholar in UIUC with Shaowen. Now I give the presentation about spatial temporal clustering of behavior trajectory based on data fields. Here is the outline. Introduction. Now we can acquire many trajectory data, including some trajectory points of floating cars and some trajectory of volunteers. For example, we can give some waist watch to some volunteer to connect their trajectory, and some route networks is the base map of their trajectory analysis. There are many taxis in some big cities, especially in China. For example, in Wuhan city, there are 97,000 taxis. We can now we have collect their GPS data of the taxis. We can collect their GPS point for each for every taxi for every 50 to 60 seconds. All the data are very huge. Maybe it become a spatial big data. So for this data, we should do some research. It needs some spatial big data technology and some CyberGIS technology. For this research, we aim to the problem: how to extract information and discover knowledge from such spatial big data, which can be saved for urban planning, urban management, or daily life. Of course, there are many kind of knowledge we can discover it from this data. The research focus on the aim, how to explore some spatial temporal clustering patterns. And our method is data field. Data field is a theory which introduces some theory from physical field. I will introduce this theory in the next slides. And two experiments are carried on by us. One is the extraction of traffic congestion regions. Another is the detection of get-on and get-off hotspots. Now I will introduce the data field theories. As we know, physics is a great science. There are many theories in physics. So we hope to introduce some theories from physics to data analysis, and introduce them to GIS to put forward some new theories for spatial analysis. And for example, physics field is an important theory in physics. It can be used to describe the interaction between particles. There are many physical fields, for example, electric field and nuclear field and so on. Here is an example. It's a data field, which is put forward by Professor Devin in China. He put forward the data series concept. It means give a data field produced by a set of data objects in space sigma. The partition at any point can be calculated as the following formulas. Maybe someone will say it similar from some other method. For example, the KDE, the color density estimation. But the data field is from another volume point. It's a try to introduce some theories in physics to data analysis and GIS. Maybe in the future we will introduce more theories from physics to the GIS. Maybe it will produce some new theories and new methods. And therefore, there below three figures are some example. It's a data field for 1 point. It produces some equal pertension lines to describe the interaction of the point, and the data field of 2 points and the data field of 13 points. For the data field, we can produce some spatial clustering method. Here is an example. It's a clustering based on the topology of the pertension of data field. In the upper left figure, it's a data field for 319 points. It produces a nested topology structure. If we select suitable potential values, potential line values, we can produce a cluster in some neighbor. For example, if we select the outside the potential line, all the data are clustered in one cluster. It corresponds to neighbor 5. If we select pertension line, for example, this line, it will be a cluster of 5 clusters. For this method, it's, if there are more density of point, more higher value of pertension, so the method combines the merits of hierarchy clustering and density clustering. Another example about a data set which includes 10,000 points is with different shapes and different densities. The result is very good. For the spatial clustering of data field, we introduce it into the behavior trajectory analysis of the taxi GPS point. We have carried out 2 experiments. The first one is extraction of traffic congestion regions. We use the spatiotemporal clustering based on data field to extract some traffic congestion region. Here are 2 examples. For example, firstly, we should define the traffic congestion points. Maybe in different cities, in different situations, the definition about the traffic congestion point is different. So based on the definition, we do some spatial analysis for the traffic congestion region. Here is the result. In order to understand the traffic region, we can give some visualization. We can say at the 10 to 11 p.m., the traffic congestion is the series. The second example is detection of get-off hotspots. For this research, we can do some travel behavior analysis. We can extract some interesting place, which maybe means many people get on or get off frequently. For example, they're below right figure. At this time, many people go out for dinner. In this region, there are many good restaurants. Some people take taxi to this place to have dinner. Now, I give the conclusion. In this research, we explored a method of spatial temporal clustering detection of behavior trajectory based on data permutation field. It's inspired by some theories from physicists. Of course, there are some shortcomings. For example, we only consider the spatial clustering at a different time, but we haven't considered the interaction between space and time. In the near future, we will do some ongoing work. One is extend the method to spatial temporal clustering. Another work is about integrate with CyberGIS gateway. We hope to find some high performance solution to to speed their processing. Thank you.
Good afternoon. I'm Devin White. I'm the team lead for scalable and high-performance geocomputation at Oak Ridge National Laboratory in the Geographic Information Science and Technology group. Try putting that on a business card, by the way. Not easy. And the second title you see there actually is not a typo. I am a fully licensed, so to speak, practicing anthropologist. So I live at that intersection between humanities, social science, and CyberGIS, in that bridge space. It's fascinating, terrifying, exciting, really interesting, and it's been a wonderful ride the last couple of years, especially working at the lab now. When Budu asked me to give a position paper or prodded me to submit one, I said, okay, I'm gonna take a position on something. And the title pretty much says it all, and I'm gonna steal David's term here, concurrent validity, I think was the term you used, yes. What I'm going to say is nothing you haven't heard over the last 2 days, and in particular, probably over the last several years as you've been working in the CyberGIS domain. But what I want to emphasize is that we're working very much on the operational applied R&D side of the house, and we're trying to push forward with a lot of what we've been talking about here. We're having our own challenges. I want to share with you some of what we found. But again, this is sort of a position paper, us putting our flag on the ground. All right. So who we are and what we do. Most of you probably know what GIST does at Oak Ridge, but I'll just give you a few seconds here of an overview. We do address global scale, rapid tempo, high resolution GI science research. And we do this in a way that directly impacts the operational missions of many federal agencies and large organizations. The nature of our work aligns very well with the classic dimensions of big data, and I'm not going to go over them here other than to say that these 4 and the other variants with other V's put on there are daily things that my group in particular and my team specifically are challenged by. And we outgrew desktop GIS a long time ago. So our 3 core tenets, and this is really where I put the position in play here. Everything as a service, pick your acronym. Everything open source, and this is very much a work in progress for us. So doing this within the national lab system is challenging. It is something that we very much believe we need to do, and we're trying to find ways to make that happen. And we also, to keep things going in line with everything, is everything fast, tightly integrating hardware and software. In terms of everything as a service, we're now building all of our products and applications so that they are accessible through standardized and interconnectable APIs. And we put lightweight, platform agnostic GUIs on top of this, mainly in HTML5. The idea is to make these as distributable and as lightweight as possible. We want to make everything available as a service in one form or another. And we want to hide the complexity and the computing needs from the user so that they can focus on their job, and to do so in a way that enables interoperability again. And when we can, we use OGC standards. But often, we may have to build our own RESTful solutions. And again, we do focus on REST. I'll give you one example of this right off the bat. It's an application called WorldStamp, the World Spatiotemporal Analytics and Mapping Project. EXTJS on the front end, D3 for the visualizations. We have Postgres on the back end. That's scaling, by the way. This system works with over 7,000 attributes for every country in the world for at least 25 years, and sometimes going back a lot further than that. It's a big data wrangling exercise, as you can imagine, but at the heart of it is the ability to actually analyze the data and say something meaningful about it. It's an exploratory engine for analysts in particular. And this is sort of an outdated graph of how the system works, but you can see there are multiple entry points to this. And we've been talking about enabling services so that there's multiple ways to get into the analytics, to the data, to the parts that actually matter to the analysts in particular. So you can come in through the front end as a user, you can come in through the side in multiple ways, either directly through R into the analytics and then to the data, or directly to the data itself. You make the choice. In terms of everything open source, and again, I do have a pin on that in terms of the asterisk, we are working on ways to contribute. We have fully embraced open source software in everything that we do to support transparency for our sponsors, to enable customization and to ensure reliability and scalability for our operationalized systems. People are using our applications every day. We don't use commercial software once we move beyond prototypes and proof of concept. And this extends from version control all the way up to our scaled HPC applications. I'll give you a couple examples of this. One, Budu mentioned yesterday, population density tables. Without belaboring the point of what it actually does, again, this is a scaled system, all open source. And in terms of transparency, every number we come up with for population density, you can click on and you can see the whole chain of where that number came from, down to the formulas and the sources we used from the open source domain to get that information. And it's also service-oriented as well in many respects. There's an API behind it. And you'll see there's this little factbook link here. It actually hooks into the World Stamp database behind the scenes to pull in context information for countries as you're exploring that data. It's kind of fun. And we also have moved into big data analytics in this domain as well by doing what we call modeled values, where let's say you have a country where you don't really have a lot of good information about population density, but all the other neighboring countries, you have better information. So using a Bayesian approach, we've been able to model population density information, and we label it as such. But we want to be able to fill in the gaps where we can, and obviously that's a computationally intensive exercise. Again, hitting an R service behind the scenes to make that happen, and the data is updated on a very regular basis. Budu also mentioned the bioenergy KDF yesterday. Again, another operational system. This one's based on Drupal. And again, open source, there's API sitting behind all of it, scalable search, we're using Solar, among other things. But at the heart of it as well, because I wouldn't be mentioning it at CyberGIS if it didn't have a map on it, is the mapping interface. Now again, this is not just for layer analysis, it's not just for context. You can bring in services from all over the web, view them on top of each other if that's all you want to do, but it also hooks into various modeling scenarios. Budu mentioned in particular one where you can model where biomass might be grown in the future based on different scenarios that you like to select and to sort of see what happens. And this is one of the outputs from that process. So instead of it taking weeks, working with National Lab staff to generate these maps, you can do it on the fly, export them. And we tried to make this interface such that the top 10, 20 things that most people would like to do with a desktop GIS we have built into this. A lot of the basic navigations, layer controls, things so that they can do all their visualization and analysis in the tool. And if they need to export it, they can, and move it into another framework, they can. And of course, everything fast. Utilizing HPC architectures to support scaled geocomputation is pretty much putting a square peg in a round hole, and I think we all appreciate that. We're trying to make it work with what we have. And I've seen some incredibly creative ways to do this. And not only in the last couple of days, but the last few years. I'm truly impressed at what we've managed to come up with as a community to make it work with the architectures that exist today. On the commercial side, it's really not much better. You have Hadoop and you have various cloud implementations. And again, we're trying to find ways to work with these systems that weren't built for our needs. And we've done a great job with that, but I think we can do a lot more. We can and should be better aligned with the broader HPC community in this regard, have them help us and have us help them in terms of finding a way to take full advantage of the hardware that's out there, and in some cases, building new hardware that specifically meets our needs. Our goal as a lab and our group in particular is to share lessons we learned from this process with the broader HPG computation community and to work side by side with them as much as we can on solutions. Thanks. I'll mention two examples where this has been challenging for us and is not going away anytime soon, and it's driving a lot of our high-performance research and development tasks. One is the spatial refinement of Landscan Global. So as you can see, you have your 1 kilometer pixels. We're trying to get it down to 90 meters at a global scale, computationally intensive in and of itself. But now we're doing this again for the entire world, so massive amounts of satellite imagery, massive amounts of computation just to asymmetrically put the people where we think they should be. Sitting behind that is Settlement Mapper. And you saw some examples of this yesterday. This in particular is old stats. It's the one I could grab right before the talk, actually. But it's an extremely efficient, extremely fast way to map built environment globally. And when we talk to the satellite vendors, the satellite image vendors about data, they say, well, what part of a country do you want? We say, no, the whole country. Well, just one country? No, all of sub-Saharan Africa, thank you. You know, we would like all of it. Just give us everything. And they think we're nuts. We're like, no, we will process all of it. And you have to do the pan sharpening, the ortho, the atmospheric correction, you name it. You start scaling this up and it gets to be a nightmare, but it's a good challenge. And we're working through some of that, working with the vendors, especially on the hardware side as much as we can, to improve the throughput on this, and again, to bring these lessons that we learn through this massive computational exercise back into the broader CyberGIS community so everyone can benefit. This, by the way, is our last remaining non-web enabled user interface. It's in MATLAB and I want to destroy it. It works. We actually are in the process of changing this over to something in HTML5. We're not quite ready to unveil that yet. But what it will do is really open up who can operate the system, because right now it's license dependent. It works on the desktop, even though it's hitting GPUs on the back end, and that's not really scalable. So we're fixing that problem. The last thing I'll mention, and again, people have talked about cost paths a little bit. That's an area that's near and dear to my heart. So this is a project called FEET, or From Everywhere to Everywhere. It's a pedestrian flow model, hence the pun, sort of. Or unless you're French, that means party, which I know we're getting near reception time, so I'll try to keep this brief. What Boodoo calls this, and I have to agree, it's sort of an interesting way to term it, is people sheds. You just wash people across a landscape and see where they go. And this is an urban environment captured in LiDAR. And what I've done is say, I don't know where people are coming from or going to. I just want to kind of get a sense of where they might go. And so you get something kind of like a heat map, and you can do this in natural or built environment. And you can imagine just how much computing power is required to do this with LiDAR at scale. Millions upon millions upon millions of paths are being calculated. And all this is infused with a knowledge on the anthropological side and the human biometric side about how people actually move through landscapes. So with that, and again, you can check out my poster a little bit later about the technologies. But this is what's in our toolbox. There's no silver bullet. Lots of different applications, architectures, programming languages. I think most of you are familiar with all of these. But we're trying to be more open about the tools that we use and the software that we adopt. And so I encourage you to come by and ask questions. Thank you.
Let's give a hand for all our presenters. So any quick questions? Please, presenters, please come up. Questions from the audience. Yes, please, Wendy.
Simple question to the last image we just saw, the washing people through the landscape. Is that landscape DEM, or is that landscape peoplescape, meaning population density?
It is actually physical landscape to start. That's the base, but you can layer other types of information on top of it, land cover, population density. We're experimenting with other ways to drive the sorts of decisions the agents are making. I'm using the term agent loosely in terms of how people are moving. But the physical terrain is the start of that landscape. And then we put other information on top of it and have the algorithm sort of decide how people might want to move.
Further questions?
Speechless.
I also have a question for the last presenter. In the imagery you showed us, how can you detect, people's movement from the imagery? Can you elaborate on that again?
So the question is, how can we detect movement from satellite imagery?
Mm-hmm.
I'm hoping I didn't misrepresent that. We're not actually detecting movement through imagery. I mean, there's full motion video analysis that can do that, activities-based sort of work, computer vision, obviously. What you saw right there at the end, this particular graphic, is done using massively scaled least cost path analysis. So what we're doing is generating a probability surface of where people might go. One of the things I would love to do with this is to go get things like fitness tracker information, put that on top of it, and see how it actually lines up. Again, this is more for scenario planning, disaster planning, emergency response. This actually is a part of Port-au-Prince in Haiti. and I wish we had had this sort of technology available right after the earthquake, because once their infrastructure broke, LiDAR was flown, and this sort of technology gives you the opportunity to try to reconstruct how people can move around in that new environment where even the open street mapping that was going on wasn't quite complete yet. And you at least can get a sense of what's possible and plan off of that. So we're not directly detecting travel. What we're doing is trying to indicate where people might be. In a sense, yeah. What we're looking at here is the potentiality of where people could be based on the built environment and other information layered on top of it. So, didn't realize that one graphic.
So I have a question for Qin Kun. So yeah, I was very interested in the hot areas of traffic detected from the taxi data. So I was just wondering, do you plan to validate the result? So is there any way to evaluate whether the hot traffic congestion zones are correct or not?
For the hotspots detection, we do the research, find some interesting place. We use the spatial data, spatial clustering method to find their place. Many people visit frequently. Maybe. And let Junjun or me could answer the question.
I could add to that, maybe. So the idea is this is very hard to validate. What we're currently experimenting is to use synthetic data sets to compare with similar methods, such as a DB scan, see how much this is off or on the targets, to do on-site detection given the dynamics of traffic situation. We found is extremely challenging, and also data accessibility is another issue.
Thank you, Shaowen. Final question.
I have a question for Junjun Yin. I think you did a nice job in using the satellite imagery to detect the natural city of the human population. I got a question about the first, what's the resolution of the imagery? And the second one is, within a pixel of your satellite imagery, I believe there should be a minimum number of lights that exist in order for you to detect them. So do you have any idea about how many, at minimum, how many lights should there be in order for the imagery to detect, the lights?
Okay. The resolution is 30 meters, I think. Resolution in terms of 30 arc or 30. I just remember the number. But for the value, so once the NOAA, the organization, obtain the nighttime light image, they do the adjustment from the value. Like sometimes there's a fire, like the value can be extremely high, so they do the adjustment already. So the range will be between 0 to 63. I mean the image value right now, from the darkest to lightest, will be 0 to 63. And how to choose, like which is the cutting point for this value, right? To choose the area like we want to keep. Right now we're using another concept that developed with my master degree supervisor. We had this called head-tail break, head and tail, like so. Because we still think, if you count the values all over the globe, you still get a very high, heavy tail distribution. So that means the very low values, the very high values, very extremely small, like small in terms of percentage, and then all the rest of them are are the common ones. So they use that mean value to cut, which is right now we're using 23. Mm. Yeah, 23 to 63, I think. Yeah.
Let's thank our speakers again.